All right, good afternoon, everyone. Please settle down. Ideally, towards the front side of the room, not the back side of the room, if possible. So today, it is my pleasure to welcome our Jones Seminar Series host, our guest, Dr. Ruan. He is currently a postdoc at the Laboratory for Information and Decision Systems, or LIDS, at MIT. And he got his PhD in electrical engineering from Tsinghua University and a postdoc from University of Hong Kong. He has won a number of awards, including outstanding reviewer for many prestigious journals, such as Ultimately Transactions on Power Systems, Ultimately Transactions on Sustainable Energy, as well as being selected for a cohort of Future Leaders Summit held by the University of Michigan. His research is in AI for sustainability, learning for control, electricity markets, energy storage, and demand response. So please welcome Dr. Ruan.
Thank you. Okay, thank you so much for having me. And then also I would like to thank Vikram for the introduction. And I would like to thank Amos for taking care of my logistics. And also really happy to be here. This is my first time here and I just feel really welcome. And I got the chance today to meet some of you, some faculty members, and also some really talented students. I feel like it's a really exciting time to meet all of you and really happy to present some of my work today. So so today we are going to talk about grid aid control. So it's mostly in the context of energy system. And if you have been interested in the energy sector, you may have the chance to heard about this term, grid age or grid age control. But you may want to know what exactly it means for like grid age. And then, so today I will going to share some opinion about this grid age and grid age control. And also I would like to tell you the special role of this grid age control, especially in the future energy system. So today, that's a plan for today. We are going to talk about grid age and grid age control at the very beginning, give you some high-level understanding of what is the question, what is the problem, and why we care about this, and why we feel like there is a kind of a paradigm shift in understanding the future energy system. So, and then I'm going to narrow down it because that's a really broad topic to talk about grid age. We're going to narrow down it to two use cases. So the first one is about EV, electric vehicle, and we talk about the resilient charging of electric vehicles. And then also, in the second use case, I will going to talk about the flexibility market part. That's how do you design a good market to incentive the end users to behave in a way that the system wants. And finally, I will sum up with some challenges and opportunities. I think I have more slides today, so maybe I will go really quick when I find that I don't have enough time. But let's see. Okay. So let's go to the first part, the rise of the grid age control. Okay. I borrowed this figure from the internet. Just want to show you that if you think of the future energy system, it may look very different from what we have today. So we are kind of in the middle place. But the thing is that in the future, we are going to have more and more renewable energy, and then also more and more electrified demand. For example, like electric vehicles, like heat pumps, that's happening now in the New England region. And from there, you will find that we have more and more different resources in the network that might look different from the previous. So what does that mean? So we will briefly say that there's several changes in the energy landscape. So first is that we will have increasing penetration of the distributed energy resources, or DERs. We will keep talking about DERs in the whole talk. And this can include like solar PV, like the wind turbines, residential battery, EVs, demand side management. They can be a lot of elements, but all these elements, we're going to have a really large scale, but maybe small sized resources. So the problem is, if you have all these kind of resources, how to control them, how to schedule it in the future in your system? And also, because there are a lot of this kind of generator, like the solar and the wind, then we will see the decentralization of the power generation. And also, because of the widespread electrification, we are going to have more higher demand, or this demand can be really flexible, and it can have some control based on them. And also, for the grid edge intelligence, we are going to have more smart meters. We're going to have IoT devices. So it's possible for us to do some better control, just like AI-driven control for this localized decision-making. So this figure is a standard IEEE 30-bus system. I guess some of you should be really familiar with that. We have a category of this kind of standard system in this community. So in this figure, we are showing that we have a lot of generators, but that's mostly the thermal generators. That's really large scale. And then we have several transmission lines. But if you are seeing this diagram carefully, actually, what I mean by grid age is simply this. Okay? It's just an arrow. It's an arrow symbol in the figure. That means we don't care too much about this generator, this transmission line. I mean, they're also important, but we have a lot of discussion on that in the past, maybe 30 or 40 years. But now, what is changing and what are the most exciting energy innovation happening is actually not at the generation side or transmission side. I mean, there's some, but many of the innovations are happening at the demand side, or it's just this. So in the classical, power system operation, we will just formulate some energy balance formula. So it's the simplest version you can get. It just means the power generation should equal to the power demand. But of course, in this system, you can expand it by having a lot of different this kind of equality constraint to say the power demand and the power generation should be balanced at each node of this system and also at each hour. So we can expand it by like a PJ, summation of PJIT should equal to DJT. Like J is just the precision or the node this demand is located at, and also T is the time index. So we can expand it, but here for simplicity, I just use this one, and then we will revisit it maybe in 3 or 4 slides. But that is the classical thing we have in the classical view, and actually in our analysis we have fixed the demand. So this here, the expectation of the demand is a fixed number. It's just a number. You can do the load forecasting to get this number, but it's just a number. And then we are doing a lot of computing, like powerful calculation or this kind of unit commitment, economy dispatch, trying to decide what is the power generation we should get. So that is a classical power system analysis. But when we have more and more DERs that's distributed energy resources, and if we say this demand is going to be flexible or it's kind of like controllable, then we should rethink about this framework we're talking about. In other words, here, D is no longer a fixed number. There should be some decision variable inside, and then that's why we need to do this kind of a modeling. So we can zoom in a little bit for this. So if there is really high-level kind of abstraction of what we have, if you zoom in a little bit, actually, that is the system you will have. So we have the bulk power generation, and then we have the transmission system and also have the distribution system. So DER, or this kind of distributed resources, will mostly happen in the distribution system, but some larger one can happen maybe in the transmission system. But all these kind of details is kind of not truly captured in a framework like, maybe in a framework like this. So we are kind of zooming the system to care more about this power, this grid side or this grid age. So the grid age, by definition, refers to the interface between the end user and the power grid. we're taking this part into consideration. And why that's really important? Because, if you consider the electric vehicles, you need to think about how do you design the charging. You can have some smart charging, and all these kind of smart charging control are actually happening at the grid edge. And also, if you remember that in the past, we only have demand, so you are just consume energy from the grid. But if you have distributed solar, it's possible that my solar output is larger than my demand, then it's possible that I can reject the power back to the grid. So in that case, you become a generator. So sometimes you are a consumer, sometimes you are a generator. So in the community, we call it you are kind of a prosumer. It's a producer and consumer just combined together. And we have some possible decentralized control and edge computing to make sure all this kind of grid edge is now not a fixed number. It's going to be controllable. So that's why people are talking a lot about this grid edge control. So now let's forget about all these kind of ownership problems and technical difficulties. Just think about this. So in the future, we know in the whole energy system, we are going to have more and more of this distributed resource in the systems. It's really large scale, but it's really small size. Okay, the system design question you can ask, at least there's two. The first one, what is the best way to coordinate between these large scale and distributed resources? Can we follow the same way as we control the current the power system? Maybe not. The reason is that if you think about IEEE 30 bus system, actually we have, I think it's around eight generators. We just have that kind of numbers. It's just a small number of generator you need to control. But let's say if you want to control like this kind of system full of distributed resources, maybe you need to have a way to coordinate over thousands of resources. So it's not a really scalable solution, and maybe you have a lot of computational difficulties. So what is the best way? And so that's really the first one question we can ask. The second question is, okay, so now let's say we find a way to coordinate this system. So you need to think about what is the enabled technologies, and also what is the infrastructure upgrades we have to take to help us to there. So I think a lot of grid edge control literature are kind of trying to answer these two really important questions. And today I'm going to talk about maybe mostly about how to do the coordinating, and then how to do the coordination, and also what is the potential technology you can use to do this coordination. Okay. So the transition to the electric edge grid should be the way that we should provide a scalable and also feasible solution to that. This should be different from the existing our system. So maybe an easy way to go there is to do hierarchical control, right? If you cannot control, let's say, several thousand resources, maybe we can have some agents, right, at the middle, the agents. And then we have, let's say, 20 agents, and each agent takes 50 users. That would be a really good way, and then also a scalable solution to solve this kind of problem. So we have a lot of new aggregators, or maybe VPP virtual power plants, or we have also the load entity server. So we have some new kind of members in the system, just help us to do this hierarchical control. And also, if you talk about, if you want to have this kind of grid edge control, in the past, we already have this control at a really high level, at the system operator level. And now, if you want to put this central control to the grid edge, that means we need more kind of technologies. But now it's there. For example, like the advanced metering infrastructure. Smart grid is the most important innovation in the past few decades. And then we have already a lot of smart meters in the system. And then also for the edge computing for IoT, and we have some energy systems just for the residential user. For example, today I talk about that for Tesla. If you have the battery, they have a small energy management system for you to use. You can choose what you like and how do you like the system to operate. And then it's done. So this is kind of like a decentralized energy management system. So we already have this technology in the system, but the way is that we should think about how do you connect all of them together? Because now, mostly for energy system operator, they don't actually care about DERs now because we don't have that much. But in the future, there will be another story. And also for the DER, for the kind of like the Tesla or maybe for the distributed solar companies, they are kind of don't care too much about the systems. So, but that would be a different story because the system did not send the useful information to the kind of the users. I will talk about that maybe later. So I would want to emphasize that currently we have this technology, we have this need, but they're kind of single points in the system. They are not connected to each other. So that's why we need grid edge control. We need to connect them together to make sure that we can have a really good coordination between all these kind of resources and also for the future. That would be the case, especially if you have a really large scale resources. Okay, we are going to return to this formula. So if you remember that we talk about in our standard power system scheduling, we care about, when we do the system balancing, we have fixed the demand, and then we're trying to optimize the power generation. Okay, you need to decide how to schedule the power generators such that we fulfill all the demand. But now, when we have more and more DERs, we should think about how we balance the system, maybe in this way. So there's just a formula I show you here. The first thing is that we are going to have some distributed generators in the demand side as well. The generators can come from the demand. For example, it just can just be the solar panels on your rooftop, or it can be a battery you have in your house. So we are going to have more and more distributed generators here. So demand can look like this. And also, more importantly, is that you can have some control at the grid side, at the grid edge side, such that we are able to introduce some change of the demand or of the distributed generator such that we have this flexibility. And this flexibility should be the function of two things. The first one is lambda. Lambda can be some control signal or some incentive signal, just like price. So that is something that your system operator can send to the users. But of course, what is the best signal you should send? And that's some technical question, but generally, when we have some controllability at the grid side, we are able to use some lambda to control the possible flexibility we have in the grid side, in the grid edge. And also, I want to highlight that our flexibility is not a fixed number. So a lot of literature, they will assume that, okay, you have like 5% change of the demand. So that's the overall thing you can have. But actually, I will show one example to show that this flexibility is highly associated with what control you take at the grid edge side. And also it can be influenced by the environment variables. So I will give a really concrete example what I mean by this. So in the following two use case, for the EV charging part, I'm going to show you that how can we consider this kind of environment impact of our demand flexibility. And then for the second part, I will just show you, okay, in one case, how can you design the coordination signal between the aggregator and the end users. So that is what we are going to talk about in the following two sections. Okay. Okay, so before we go into the use case, any questions so far? Okay. Okay, no, perfect. So let's go to the first use case. The first use case is resilient charging for the electric vehicles. Okay, the question I would like to ask here is, does our EV smart charging fit all temperature? So maybe just give you a bit context. So what is smart charging? Smart charging is kind of a control you can take on the charging station. Okay, so let's say we have a time varying price. So there's a price signal that can change maybe every minute or every hour. We have this signal. So the charging station can decide when to charge the EV batteries. So usually you just charge when the price is low, and then I can stop maybe for 2 or 3 hours when the price is high, and then I can recharge again when the price goes down. So that is the smart charging. So you need to take care about, let's say, if the EV is going to located in the garage for, let's say, 6 hours, then I can decide in this 6 hours, what is the best time I should charge this battery. Also, we can design what is the charging power you take. So that's smart charging. Okay, so the question here is that, so when we talk about smart charging, is it this kind of smart charging scheme useful for every temperature cases? So I think the question is no and yes. So why I say no is because when we design the smart charging, actually, we don't care about this temperature stuff. So when we do smart charging, the objective is to minimize the total charging cost. And then you have some constraint, physical constraint on the battery or maybe on the system side, but you don't actually have a variable to show the temperature of this battery or anything. So we don't actually put this thermal consideration in our smart charging problems. But I would say yes. The reason is that the current electric vehicle, they have this thermal management system. So whenever they detect that, okay, the temperature is below a preferred temperature, they will just get started to heat the battery at once without caring about any of the price, something. So in other words, we have energy management system, we have thermal management system, but these two systems, they are kind of not work together, you know? So now what's happening is that the thermal management system will just keep running if they find the temperature is lower than expected. And then you are taking another smart charging design for the energy management side. So they are kind of parallel. I will show this later with a figure. Okay. So in this research, I would like to show that temperature should be taken into consideration, especially, you know, in the New England, because we have a really cold winter. So in the winter, you need to make sure that you always keep the temperature of your battery. If you're going to charge your battery at a really low temperature, you're going to kill your batteries. Maybe just charge, and after 5 hours, your battery is done. So that's really possible. So that's why we need to take this temperature consideration in our decision model. So here, I will just show maybe some background. So first is the cold climate. What do you mean by cold climate? So that's a prolonged period of excessively cold temperature. So usually, you know, that can be different kind of definition, but people will say, okay, temperature below freezing can be taken as a cold climate. So around the US, there's a lot of this kind of cold climate. So you can see in the central New York, 1/3 of the time, that's kind of, we have the sub-freezing temperature, and that we have like more than a month that is all day freezing. That's all, the higher temperature is below zero. And even in Texas, in the North Texas, you know, you have some time that you have really cold temperature with 32 days with sub-freezing temperature. So it's really widespread. And also cold climate, we have a devastating impact on the battery performance and lifespan. There's for example, there's at least two bullet points here. First is that because the cold temperature will increase your inertial resistance, then you will have reduced charging efficiency and longer charging time. And then also that will reduce your driving range, also that will cause some lower battery capacity. One word that is really bad for the battery. So you should always think about to keep the good temperature for the battery before you do charging. So now in most of the electric vehicle, we have this thermal management system. We have a different way to keep this temperature. We can do self-heating. We can do another, like the convention-based heating. So all these things are really workable, but just come back to this. So, but now what's happening is that thermal management system, is mostly developed on parallel to our energy management system. That is okay for many use cases, but when you talk about the electric vehicle in some cold climates, we should think about this. We should think about maybe another way like this. We should put this thermal management system into consideration because actually they have a really high coordination in that case. So, and also the objective of this part of work, I want to show you that when you think about grid edge control, when you think about the flexibility of the demand side, how do you do the control and what is the external environment look like has a really high impact on the final flexibility. So let's be more specific on what I mean by this kind of system. So now let's consider a charging station, and then we have several electric vehicle here. We have the grid connection. So if you do not have enough, so also we have the solar panel, rooftop solar panel. So if the solar is enough, then I will use solar energy. If solar is not enough, then I will get energy from the grid. So my goal here is to charge all the vehicles, okay? So that's my problem here. And then we are going to take this thermal management system into consideration, but we will assume that the thermal management system is also controllable by our charging station. We are not there yet because now the thermal management system is more closed. It's just coded in the system, but actually, if we open that API, it's possible to do a coordination. So many kind of some use case would be possible, like we can consider some battery swapping or some dedicated charging station. Maybe they care about how to improve the efficiency such that we can have better battery performance. And also, there will be some communication service companies. But I would just want to show that we are not already there, but this is something that we can think about. So let's go to the model we have. Okay. So we are going to minimize, so this objective function, we are going to minimize the total energy cost. So here, that's an assumption that if you are using solar, then you don't need to pay anything. That means we assume that there's zero operational cost. It's roughly right because the cost is really marginal. And then we don't consider some vehicle quarreling, so that can be extended in our kind of future work. Also, we don't consider network constraints, so it's just kind of more like engine management system. So by minimizing the total cost, we also need to consider a few constraints. So here I just list some. So these constraints are just really classical in the EV smart charging paper. So we consider energy balancing. So the energy can come from solar, and also it can have some energy from the grid. So we need to make sure that all this energy generation should equal to our demand. So demand now is split to two parts. First part is the energy used for charging. That's the first part. And also there's another part that's energy you spend to heating the batteries. And then we have some upper bound for different variables. And also we have an upper bound for the total energy injection from the charger, because usually you have a kind of capacity for the charger, so that we have a kind of upper bound here. And then we know when this vehicle will be in the charging station. So if the vehicle is, if not at that time, that we will assume that all the power should be zero. And we will have several constraints on the battery. So SOC is the state of charge. That means how much energy is inside the battery. So we are going to consider so this part is going to show if I give a charging power, what is the SOC, or what is the change of the energy in the battery. And then so the SOC is here defined is a number within 0 and 1. So this is all classical setup for the model. And there will be some coupling constraint. That's the most interesting part in this work. So we should have some coupling constraint between charging and heating. And I will just show more details how we formulate this kind of constraints. Before that, I would like to show just a figure to just let you know where the coupling come from. So basically, we have the charging demand, P charge, and we have the heating demand, that's the P heat. And then for the charging demand, we are going to change as how much energy is in the battery, so we are changing SOC. And for the heating demand, you're going to change the temperature of the battery, So a little bit more context. So here, I means the index for the vehicle, T is index for the hour, and then and omega or W here is just the index for the scenario because we consider some uncertainty. So we use some scenario-based modeling for the uncertainty. But there's some details. I just want to show you that, okay, so there's a lot of connection between them. And also, if you give me a temperature, we will know what is the largest charging power you can get. So for example, if you are in really low temperature, you cannot charge too fast. The charging power should be really limited. So there's some coupling between that. And then, okay, so to sum up, we will basically have two types of coupling. The first one is battery thermodynamics. The second one is temperature sensitive charging. So what I mean battery thermodynamics mostly how, so if you have the charging, the heating demand, and also the charging demand, how will that change the temperature of the battery? And then the second part is that, okay, I give you a temperature, what is the impact on the allowable charging demand you can have? So let's consider the first part, the battery thermodynamics. We consider a first order system, so it's a kind of a simple one. So let me see if I have, yeah. Maybe go back a little bit. So the main part is about first equation. So it's just a simple thermal equivalence. So we just show the change of the battery temperature is a function of several active power injection. So first you will have some, let's put it, okay. You will have some heat insulation measures so that we can keep the temperature. And also we have two parts for the energy injection. The first part is that we have some power used for heating. So this power will be beneficial to increase the temperature of the battery. And also, for the charging part, actually, you are not using up all the charging power. Maybe use, let's say, 90% of them or 95% of them. So you will have some waste heat. So this waste heat will also be helpful to increase the temperature of the battery. So that is the dynamics I'm considering in the battery side. Okay, and then there's one constraint here I highlighted here. So this constraint just describes the heating capacity changes. So here the thing. So for most of the heater in the electric vehicles, actually it's not a fixed frequency. It's not a fixed efficiency. So the efficiency is changing according to the temperature you have. So this is true for different kind of technology you can use in the electric vehicles. The most popular tool is the PTC heater. It's just like a resistor, and then you can put this resistor on your battery, and then you just input the current, and then you get some heating power from there. Another is heat pump. Usually use heat pump also with the whole air conditioner system to provide this heating power. But for any of these two options, actually you can see that the heating capacity is changing. And then usually if you have a higher temperature, your heating capacity can be lower. So that's why we kind of have this kind of negative relationship between the upper bound of your heating demand. Okay. So the second part is that when we know the temperature of the battery, what is the possible charging demand you can put on this battery? Because as we said, if the temperature is low, then you should not charge too fast. So there's several things. So the major constraint here is this part. That is somehow we are showing that if you have a higher temperature, it's going to be possible to give a higher charging demand. and then we use the linear function to capture that. Actually, in reality, you can do a lot of experiment to estimate the possible parameters in these constraints. And then we introduce another constraint here at the second part. So this is a kind of like a rule-based things now happening in most of the electric vehicle. That is, when the temperature, for example, when the temperature goes down below 15 degrees, then we should not charge. So, or you should put your charging demand to a very low level. So that is kind of like the best practice in the electric vehicle industry, that they find that 15 degrees is a kind of a threshold, and if you're lower than that, you should cut down your charging power to maybe like a half, 50%, or maybe lower, or maybe 10%. So that is their practice. So we are using this 3 constraint to showing that. So the idea is that we have a binary variable v. So whenever v is equal to 1, that means we are upper bound by these smaller numbers. Otherwise, if v equal to 0, that means we don't have this constraint, then this this constraint is relaxed. So we are showing that when the temperature is really low, actually, the v will become 1, and then you will have a constraint upper bound by, let's say, 50% of the capacity you have. So that's why we formulate this model. Okay. So, okay, that's, okay. So I just want to give you some insights why we care about this. So actually, most of the damage on the battery is happening in low temperature. So that's why people come up with this kind of constraint. It's conservative, to be honest. It's really conservative, but it's programmed in the current battery management systems. Yeah. Okay. So with that, we are possible to formulate a mixed-integer linear program. So it's a really large-scale optimization. And then most of the constraints are linearized, but we have some binary variables. The binary variables mainly because it's mainly because we have this rule-based control, because we don't allow really high charging frequency when the temperature is really low. So that's the binary variables. And then if you look at the constraint matrix you have, you will probably get this kind of image. So it's really have a block structure. We have a lot of constraint based on one vehicle. So for vehicle 1, you have constraint like this, and then there's no kind of dependency between different vehicles. So all these other elements should be 0. It's true for vehicle 2 and vehicle 3, vehicle 4. And then you will have a coupling constraint. So what is the coupling constraint? The coupling constraint, if you remember, is the system energy balancing, that we sum up all the charging demand, all the heating demand from the electric vehicle, and then we ask the solar output and the energy you get from the grid to be equal to the demand you want. So from there, you are sum up all the vehicle demand. So that here, from there, you will have, let's say, a lot of 1 in this row. So that is the coupling constraint. In conditional to, so beyond this coupling constraint, all the other constraints are vehicle-wise constraints. So this structure truly is really special, and is also really common in the decarbonization kind of work, that we can introduce Ruan multiplier, or the dual decomposition, to help us to decompose this kind of problem into a bunch of small size problem. So there's some detail how we do that, but basically, finally, we want to do the following. We want to do some optimization like this. So now, this is optimization for only one vehicle, because now we don't have I, right? You give me I, you give me the kind of which vehicle you want to decide, and then I will optimize this problem. So there's a problem for vehicle I. And then we have upper layer. So this upper layer is going to design the penalty variable, or the Ruan multiplier you introduce. And then here it is the alpha. So we are going to have this alpha updates in this layer. And then with this alpha, you can do this vehicle-wise optimization. So now, to keep it easy, so we have a really large scale problem to solve. You can do that, but it's too slow. So that's why we want to accelerate. And our idea is that we introduce a dual decarbonization in this system. We use this alpha in this model such that we are able to solve kind of interruptedly of these two kind of models. So this is a really simple model, just some updates. And then at the lower level or here, you are going to solve the optimization problem for each vehicle independently, okay? But here you are going to take alpha t here. So the alpha t is also updating, so there's some iteration between each other. But what is the benefit for here? The benefit is that actually this model is much smaller than the original model. So we will show in the simulation that actually doing this can be really beneficial in the computational perspective. Okay, so there's some detail how we do this reduced order dual decarbonization. Okay, I will just skip that. I will going to show several simulation results. So now we are consider a really simple case of two vehicles. There's only two vehicles, vehicle 1 and vehicle 2. And then we are going to consider three possible charging schemes. The first scheme is what we have. So there's temperature control smart charging. So the first line is our approach. That is, we put the thermal management into our decision of our smart charging. And then we have some other possible way to do that. So the smart charging heat is like the following. So smart charging and heat scheme, you just do smart charging decision. And based on your smart charging decision, I will decide how to prepare the battery. So for example, if you want to charge at some point, that I need to do the second step as the heating decision. The heating decision will make sure the battery temperature is going to reach the preferred level of temperature. So we do kind of like two-step optimization. We do smart charging first, and then we do thermal management. So we do in two steps. And for our approach, we put it together in a unified decision model. And there's another one called instant charging and heat. So instant charging and heat is the following, is that whenever the vehicle comes into the charging station, I will just hit it and then charge it at once. And then until I finish that, I will just stop. And then if there's two vehicles in the system, I will just give them one half to each one. Okay, so that's a kind of a simple strategy we can have. So that's what you can get from this simulation. So you will find that actually the best way to do this charging is the following. For the vehicle one, we are just continue charging and heating at once, because when the vehicle comes to the charging station, the temperature of the battery is good. So I want to use this thermal inertial for that. I don't want to charge later and then let the battery cool down. So for the vehicle one, I just charge at once. But because you need to a really high charging demand for the vehicle one, then I kind of like wait a little bit for the vehicle two. I just stop a little bit, and then I get the full kind of charging for the vehicle two later. So that's kind of some kind of shifting for the demand. And you can see that if you are using some smart charging, you will always keep the temperature. But if you see the overhead rate, so what I mean overhead rate means the charging demand you spend on this system over the total energy you spend. So we want this overhead rate to be 0, because actually we don't actually need the heating demand, right? So if that's 0, that means all our energy go to charge the battery. That's good. But if that's 50%, that's pretty bad. That means half of our energy is wasted to heat the battery. So if you see this number, you can find that you get kind of the minimal overhead rate for our scheme. So we also test more cases, especially some more large-scale cases. We compare the centralized optimization and what we get from the decentralized optimization. And then the thing is that if you give let's say 30 minutes for the solving time, then actually decentralized algorithm can give you a better result. Okay, that's for the first part. I will go really quick for the second part. But here, just a summary of what we have. So I want to say that charging and heating are strongly coupled in the cold climate. It's okay if in the regular temperature, but in cold climate, they are coupling. And then with some well-developed coordination, it's possible to reduce the cost by 10%, up to 10%. And then also, we find that thermal management is really important. And then you need to have more realistic modeling in how do you charge this battery. So that's the first part, but maybe before that, any questions or comments? Yes?
So this is the two-stage stochastic program, is that correct?
It's one stage. It's one stage. But you can do two stages. So the two stages is that you design the charging first, and then you design the thermal management. But in our framework, we want to do it in one step.
So how does uncertainty materialize in this case? Maybe this is a stupid question, but
yeah.
So a scenario is defined as what, the entire time period?
Yes. And then the uncertainty comes from the solar. So you have a kind of different scenario for the solar output. And then that will be the scenarios or the uncertainty we have in the model. And then we want to make sure that at the worst case of this scenario, the system is going to keep the good, it's going to satisfy all the charging demand of all the vehicles.
So I guess my question is, what decision is made before the uncertainty?
Oh, yeah. So this problem is mostly a day ahead decision. So we are designing one day ahead, and then you can do some prediction for the uncertainty, and then based on that, you make your decision. So in real time, if the solar output is different from what we have, then maybe you can do some real time adjustment for the difference between that. Yeah. So we are. Yeah. We are not taking the expectation for the temperature. Actually, we are consider each scenario, and then for each scenario, I will give a temperature curve. So here, I just show the uncertainty, but actually we have, let's say, if you have 100 scenarios, then I have 100 curves. But I just show the upper and lower bound for that. So that's how here. But actually, we don't take the expected temperature curve in our model. Yes, it's possible. It's possible. But yeah, in this work, we don't use learning. But for the second work, I will talk about that. How can we use some learning? Thank you for the comments. Oh yeah, we don't consider that. We don't consider the power loss in the network side. So it's most like energy balancing at the charging station level. So that's not a lot of like long distance delivery. So the power loss, I think, is manageable. Yeah. Thank you. Okay, maybe I will just go through really quickly about the main idea of the second part. So for the second use case, I want to show you that now we know that you are able to control this distributed resources, but how can you design a good coordinating signal, or what information you should share to the user, and then to make sure the user behave in a way that you want, right? If you are sending some wrong misinformation, then maybe user will react in a really bad way, then that totally harm the system. So now you need to understand how do you design this information exchange between these two layers. And that's also really important in the market design, because now we're going to talk about how to use a price signal to coordinate between the user and the system. So I'm going to narrow down to this kind of really simple cases. So there's kind of a retail market, think about like that. We have several flexible users. So this user can be electric vehicles, can be batteries, can be, industry, anything. But we assume that these users have some decision models. This decision model, we assume that's convex. But we assume that for the retailer or for the aggregator, you don't have access to this model. You know this user are making decisions based on some model, based on some convex models. And how can they come to a final kind of demand, there's the following. For the retailer, they will just broadcast a possible price for that. And then the user will just respond by how much energy he would like under this price. And then the retailer will, based on this, you can sum up all the demand and just to check the system constraint. For example, here, system constraint is just a capacity. So we hope that the total capacity is not going to go beyond the limit. So it's probably that for the price, if there's a one moment that the price is really low, that everyone wants to use energy there. And then you will have a really high demand at that point, and that you cannot satisfy this constraint. So you need to carefully design how to change your price signal such that the user will kind of have the total demand of the user is going to satisfy the system constraint. And then everyone's happy with that price as well. So this is a kind of a problem we have. And then now we are focused more on this kind of interaction between retailer and the users. Let me check if okay. So I would just, maybe that's too much math, but I will want to show in this one. So if you are familiar with that is a distributed optimization, that we do some really similar thing as I described in the EV paper, that we are going to have a model like this. So this is an individual model. So each user will solve this individual model. And then you will design the power demand, that's PIT, based on the price you give me. So the lambda is the price the retailer will send to the user. And then I'm going to update this price signal gradually. So based on what we have from the user. So now, so the user total energy demand is this, the summation of PIT. And then CT is the capacity I have. I will just calculate the difference and give a kind of penalty on that. And then in this way, I will update my price signal. So the goal is that I will gradually update my price signal until all the demand is going to satisfy our upper bound. So that's the main idea. The problem is that for the update of the price, it's really hard to design a really good step size. If you are too radical, that means you pick a really large step size, then it's really possible that you get this kind of fluctuation. But if you are too small, then the convergence can be really slow. So we are thinking about what is the best decision you can make in this setup. Maybe I will just show this part to you. So the problem for the original setup is the following: is that every time I just pick up the upload of the user, so the user just told me how much energy they want to consume. So that's a PIT. I just pick up these numbers, I sum them up, and then I use that in our decision models. But actually, when you change the price a little bit, this P should be changed. So in this world, we are thinking that is it possible to let the retailer have some ability to focus what's happening if I design the price. So that's the thing. So you would decide, okay, if I change the price too much, maybe the user will just reduce too much. Then I can kind of return back a little bit. So in this way, we feel like it's more efficient for the retailer to design the price. So that's why in this framework, we are adding something here. We are adding some neural network in there. So the neural network is going to learn what is the potential response of the user. And then with that, we are able to formulate some model to design what is the best price I want to take for the next round. I will just quickly go to, so there's some details. Maybe I want to stop at, let's say, so there's some detail here. So if you do it that way, so now I have some neural network to predict what is the user demand after I take some price. So that is, here is a neural network output. Then you will find that your optimization model is going to be a hybrid model. So in this model, we have some, linear constraints, but still you have some neural network or really complicated model in your objective function. So in this world, we are trying to see how can we solve that. We propose part of like the two-stage solution. And then the first one is that because neural network is really hard to take the gradient is not really stable. So we take the bisection method. And then based on that, we are able to get a good solution there for the first stage. So why we have to change to the second stage? Because neural network can perform worse when you goes on. So you perform better in the first phase, and for the second phase, it's not going to perform really well. At that point, we would just change to a fixed step size. But the level of the fixed numbers is depending on our historic decision we take. So that's our kind of design for that. Okay, I would just jump the simulation, but I would just want to let you know that that's truly helpful to cut down the iterations between this retailer and the users. Okay, so maybe I would just sum up really quickly. I think I have taken most of the time. So for the grid edge control, actually we have a lot of challenges. The first one is that the privacy, because usually when you make decision model, you need the use demand model. And then sometimes you will assume that we have this demand model, it's really accurate demand model, but actually in real world, it's really hard to get it and sometimes really sensitive. So that's really one problem. Then we should think about maybe there's a really good way to do some privacy preserving decision in this framework. Another part is the align the dynamical performance. The thing is the following, that we only consider some minute level decision, but there's a lot of diverse timescales. You should consider the balance in millisecond, hourly, monthly, and seasonally. And to this kind of response of this grid edge diverse is totally different from the synchronous generator we have today. So we need to make sure that we can align all this performance at different timescales. The third part is that in most of these DRs, it involves people. People sometimes make stupid decisions, right? They are not always really reasonable. So in that case, that means we have more complicated behaviors. So that's why maybe machine learning will be helpful. The learning will learn the user behavior from the history data, and that might be the best guess we can take. So I think I'm going really quickly to that, but I would like to sum up here. So we want to say that decentralized and hierarchical decision making is the future. That's especially in the future energy system where we have more and more large scale and small size and resources. And the second thing is that for grid edge control, it truly provides a kind of different way to balance the system and then to mitigate some risks we have. And also, it's really important to think about what information you need to exchange between this grid edge resources and the system operator. So the market design and the public policy is really play a really crucial role in forming the kind of incentives and also dynamic pricing and also the transition energy solutions. Okay, with that, I would like to stop here. I think I'm a little bit on time, but I don't leave too much time for the Q&A. But this is the two papers about the two use cases I talk about. So if you are interested, so feel free to download the paper, and I'm happy to take any questions now. Thank you.